All right, we're back with Stan Gibilisco's Teaching Yourself Electronics, and today we're going to be talking about how diodes are used. We've already had a little glimpse about how diodes are used, but I want to cover a little bit more detail. As I told you, we're going to be going through most of this book for our Beginning in Electronics series. As of most of the books that I've reviewed, I feel like this one is the most helpful in reviewing electronics. So we're going to use this one as our primary source going forward. Okay. So today we're going to be talking about diodes. So how diodes are used, we talked about the rectifier, we talked about rectification. The reason why we talked about that, like I said, we jumped a little bit ahead, that's because we're working on that power supply, okay? Haven't forgot about that. We're still working on it. I was actually working on some schematics today. I'm going to keep working on those and have something to present to you guys. Then we'll build it and eventually probably even have some PCB boards printed out and maybe even some giveaways or something like that. Though it would be more meaningful if you made it yourself, especially if you did like point-to-point soldering and you did it. It's all going to be with through-hole parts, so we can build it on a breadboard, or you can build it on like a pref board. Okay, so just getting started here on chapter 20. Now we are going to go through chapter 19 a little bit to cover some of the topics there. Chapter 19 is the introduction to diodes. So again, I'm coming into this because I know there's a mixture of experience levels on this channel. So I'm coming in this kind of a midway point to what would be meaningful for somebody who has some experience and understanding, and then also someone who's just looking for some practicality and wanting to get started building some circuits. Well, one of the main things we have to do is we have to get into our heads, get acquainted with the common diode. So, which is our basic semiconductor. Okay, so we've reviewed capacitors, resistors, transistors. We've done some of that. We reviewed diodes too, but we also reviewed potentiometers and all these kind of components, transformers. Now the diode is where we're going to start here. Again, in this book, there is a lot of some theoretical conversation in this book, some theoretical coverage. I would encourage you to just view that yourselves. If you're that interested, we can cover it, but I'd leave that up to you guys, and we'll start with the more practical stuff. So here we're going to talk about how diodes are used, starting with rectification. So I'll read through a little bit of this, and then we'll skip in some places, and we'll talk about diodes in more detail here. So he starts off articulating the fact that vacuum tubes were the original diodes, right? And then we had semiconductors, and now today the diode is primarily what we use for that kind of function. And then what is the diode's function? Well, again, we talked about it in the last video. It's really about current flow. So what diodes do is they let current flow in one direction but not the other. Okay, so let's see here if I can get a all right, so diodes let current flow in one direction, not the other. So the arrow on the diode is there for a reason, because it's showing you the general direction of the current flow, the direction where current wants to flow in the diode. Okay, now the diode does have some signifiers here. They're not just it's not just an arrow with a line and all that kind of thing. So this side is called the anode, and this side is called the cathode. Okay, and the cathode is designated by that line there. And this is what's going to be called forward bias. I'll just put FB here. Don't confuse that with feedback. That's going to be forward bias, okay? That's our forward bias. That means that this diode generally wants to operate in that direction, okay? That's the direction it wants to operate in. That's the direction that we're using to do our rectification and all that. We put our AC signal here, and then we get DC out, okay? Let's see what Stan has to say about the diode in the rectification sense. So the hallmark of the rectifier diode is that it passes current only in one direction. This makes it useful for changing AC to DC. Generally speaking, when a cathode is negative with respect to the diode, current flows. When the cathode is positive relative to the anode, there is no current. Okay, so let's break that down a little bit, because he's using some language here that I think is particularly interesting and should be covered. So when he says that the anode, that the cathode, the diode will have a positive current flow, or will be forward biased, essentially what he's talking about when he says it'll allow current to flow. That means it'll be forward biased when it allows current to flow here, okay? When the anode is positive with respect to the cathode, and the cathode is more negative. So that does not mean that the cathode is actually has a negative voltage applied to it. It's negative with respect to the anode. That means basically what he's saying is that that the cathode is a lesser voltage than the anode. Okay, so if the cathode is 0 and then the anode is 20, then the cathode is negative with respect to the anode. So don't think that there has to be a negative voltage applied to the cathode for this to work. It just has to be less than what the anode sees. Okay, now again, as he says, when the cathode is positive relative to the anode, so that means when there's more voltage, right? So if there's more voltage on the cathode side, so if this was more positive, leaving the anode to be more negative, then current would not flow, and that's where we get our blocking feature. Basically, that's why this line here on the diode can be looked at as kind of like a wall. That means that it'll go this way, but it won't go that way. Okay, so once it tries to go this way, current tries to flow, it hits a wall. Okay, with the exception of what he's going to talk about in a second here. The constraints on this behavior are the forward, breakover, and the avalanche voltage, which we learned about in chapter 19. So let's see chapter 19. So here he has a little depiction of what we just talked about. Okay. Here's a little depiction of this. So this is the forward bias. As you can see, the anode is positive. We have a battery symbol here, and this is the positive terminal, and it's going to the anode, and it's flowing, and this is forward bias, so it allows current to flow through this resistor, and that's why you have an amp reading. It's showing a positive amp reading because there's current that flows and it goes back, and it makes a full circuit. Now he flips it over, and the cathode side is now more positive than the anode, and reverse bias, little to no current. Ideally, no current is going to flow through here, okay? Unless we hit a specific voltage. He's going to talk about that in a second. If you connect a battery and a resistor in series with a diode, you'll get a current to flow if the negative terminal of the battery is connected to the cathode and the positive terminal is connected to the anode. No current will flow if the battery is reversed, as shown in figure 19.4b. Okay. It takes a specific, well-defined minimum applied voltage for conduction to occur through the semiconductor. This is called the forward breakover voltage. Depending on this type of material, the forward breakover voltage varies from about 0.3 to 1 volt, 0.3 volts to 1 volt. That's usually talked about when we talk about resistors and the transistors and their biasing point. That's what he's talking about here. If the voltage across the junction is not at least as great as the forward breakover voltage, the diode will not conduct. Okay, so what he's telling us here is that while yes, diodes will conduct, they need a minimum voltage to conduct. The range in which he gives us from 3 millivolts to a volt here is he's kind of actually comprising anywhere down from Schottky diodes all the way to other more special specific types of diodes. The general diode, which is what we're going to be mostly concerned about, which is what we talk about mostly in electronics, is going to be referred to a 0.7 forward breakover voltage, okay? Or when we talk about transistors, we more commonly call that the bias voltage. And you can maybe see how it's implied what that would be called the bias voltage, because it biases it forward to be forward biased, okay? So it's telling it, I want to go there, right? It's biased towards a certain direction once you hit that specific voltage. So I do want to make a little note here that sometimes you'll hear it 0.7 is 0.6. 0.6 is the literal number. Most of the time is the literal number, but 0.7 is what it takes to get to over the breakover, right? So if the biasing point is 0.6, then you want to be 1 point over that, and that'll give you the breakover. So that's why it's most commonly referred to 0.7. So if you see it on a data sheet or something as 0.6, you're talking about the same thing. But when we're talking about 7, we're just talking about it being over that 0.6, and that's what will give you the reaction for it to be forward bias. If that voltage across the junction is not at least greater than the forward breakdown voltage, the diode will not conduct, even if it's connected as we show here in the forward bias point. That's what he's talking about. Even if this is connected here, if this battery was only 0.5 volts, then most general purpose diodes would not conduct. It has to be that at 0.7, and then it would conduct, okay? This effect known as the forward breakover effect, or the PN junction threshold effect, can be used in circuit designs to limit the positive and negative peak voltage that the signal can attain. The effect can also be used in a device called a threshold detector, in which a signal amount must be stronger than a certain amplitude to pass through it. That's like a signal detector circuit that we've probably looked at when we've flipped through some of these schematic books, those circuit books. So let's continue with this. We're getting some good information here. So here now he's going to talk about forward biasing here. When the N material is negative with respect to the P material, the electrons flow easily through the N to P junctions. The N-type semiconductor, which already has an excess of electrons, receives more. The P-type semiconductor with a shortage of electrons has some more taken away from it. The N-type material consistently feeds electrons to the P-type in the attempt to create an electron balance, and the battery or power supply keeps robbing the electrons from the P-type material. This condition illustrated in figure 19.5a and is known as forward bias. So let's see 19a here, if this is 19a. Okay, at A, the forward bias of the PN junction. B is the reverse bias. Okay, so you see as the on this depiction, we have the arrows going that way, wanting to be forward biased, and then in this depiction, if it's reverse bias, then we have it pushing in the arrows pushing in the other direction. There's one more thing I wanted to talk about here, and that is the avalanche effect. Sometimes a diode conducts when it's in reverse bias. Okay, so this is the other condition. We don't always, ideally, most of the time we're using diodes to be forward bias, but there's times where we might want to reverse bias them or have them be able to be operated in reverse bias, and this is what he's going to talk about here. Sometimes the diode conducts when it's reverse bias. The greater the reverse bias voltage, the more likely the electrical insulator, a PNP junction, gets up to a point. But if the reverse bias rises past a specific critical value, the voltage overcomes the ability of the junction to prevent the current flow, and the junction conducts as if it were forward bias. So let me go on here. This phenomenon is called the avalanche effect because conduction occurs in a sudden and massive way, something like a snow avalanche on the side of a mountain. So basically what he's saying here is that as I had the illustration earlier of the diode wanting to be forward biased like this in that direction, and if we had current coming in the other direction, ideally it gets blocked, but what he's saying here is that's only to a certain point. There's also a point at which if we hit a critical value of that diode, there's a point at which if that voltage that's coming here, if V over here is high enough, let's put V plus, if V plus is here, is high enough, it'll actually make its way through the diode, and that is called our avalanching effect, or more precisely, it would be reverse bias is what we would call that. And we're going to see in a little bit in situations where reverse bias is utilized. The avalanche effect does not damage the PN junction. It's a temporary thing. When the voltage drops back below the critical value, the junction behaves normally again. Some components are designed to take advantage of the avalanche effect. In other cases, the avalanche effect limits the performance of a circuit. In a device designed for voltage regulation, called a Zener diode, we'll hear about the avalanche voltage or the Zener voltage specification. So here he's alluding to what I was just talking about earlier, the essence of where you might want an avalanche effect to occur, and that's in a certain type of diode that has been designed to act in that way, okay, to act in a way that's favorable towards a reverse bias, and it actually is rated with a specific reverse bias voltage to be utilized in a circuit where you would want it to break down at a certain point. So let's say if we had a Zener diode with a like a breakdown voltage of like 5 volts, then we would know that 5 volts is when it would break down and when it would allow current to flow in the other direction. So this can range from a couple volts to well over 100 volts. Zener diodes are often used in voltage regulating circuits. For rectifier diodes and power supplies, you'll hear or read about the peak inverse voltage, or the peak reverse voltage specification. It's important that the rectifier diode has a peak inverse voltage rating great enough so that the avalanche effect will not occur during any part of the AC cycle. And this is why we didn't talk about Zener diodes or avalanching and all this stuff in my previous video about the construction of our power supply, because that's not what we want. We want the current to flow in just one direction, and that's all we want to do. Now, I have been thinking about it, and as I'm going through and making this power supply, I'm thinking about maybe if it's appropriate somewhere, I might use a Zener diode just to illustrate its usage within the voltage regulator circuit, so we can see where it would be necessary. So it doesn't mean that we'd actually use Zener diodes primarily in power situations, okay? We're just not going to use them for rectification. We're going to use them for regulation. So if anybody is unfamiliar with those terms, so your rectification is going to be AC to DC, and your regulation is a term that's used in electronics to denote a circuit that has been constructed to perform at a specific voltage, okay? Because I mean, like a lot of things in life, you know, they fluctuate, okay? So electricity doesn't want to just be at a certain voltage all the time, even though the power that comes out of your wall isn't always the same voltage, right? It's not always the same potential. When you get it into more sophisticated power supply design, or you're working with more sophisticated equipment, or you want to enhance the sophistication of your equipment, then one of the first things you're going to do is to regulate the voltage. And one reason for that is that it performs the same way all the time, no matter where it's plugged in. And also so it doesn't go over voltage somewhere where it's plugged in, because again, the power that comes out of your outlet it could be 10 or 15 volts higher than what it's supposed to be sometimes. So your regulator will regulate that voltage to where it's the same all the time. We'll walk through this quiz in another video, but I think that'll be important for us to do. But I'm going to keep going into chapter 20 here, and we're going to talk about the next use of a diode, which is going to be the diode as a detector, okay? The diode as a detector really just has to do with your basic radio circuit, okay? Let's Stan break this down for us, and then we'll talk about it. So one of the earliest diodes existed even before the vacuum tube was actually a primitive semiconductor device known as the cat whisker. It consisted of a fine piece of wire in contact with a small piece of mineral galena. This strange-looking contraption had the ability to act as a rectifier for extremely weak radio frequency currents. When the cat whisker was connected to the circuit, such as the one shown in figure 20-2, the result was a device capable of picking up amplitude modulation, AM radio signals, and producing audio output that could be heard in the headset. The galena, sometimes called a crystal, gave rise to the nickname crystal set for this primitive radio receiver. You can still build a crystal set today using a simple RF diode, a coil, a tuning capacitor, a headset, and a long wire antenna. Notice that there's no battery. The audio is provided by the signal, the signal that's received by the receiver alone. The diode in figure 20-2 acts to recover the audio from the radio signal. This process is called detection. The circuit is called a detector or demodulator. If the detector is to be effective, the diode must be of the proper type. It must have a low junction capacitance so that it can work as a rectifier and not as a capacitor at radio frequencies. Some modern RF diodes are microscopic versions of the old cat whisker enclosed in a glass case with axle leads. So basically what he's talking about here is the way this circuit functions. We have the antenna and we have some kind of tuning coil which gets the frequencies right, and we have the variable capacitor here which gives us the ability to tune the frequency to find different frequencies. And the detector here, what the diode's doing in this situation, so a radio frequency has a carrier frequency. The carrier frequency is what carries it through the air through long range. And that carrier frequency is mixed in with, or that audio frequency is mixed in with the carrier frequency to get it to a receiver. This being our receiver, what the job of the diode is in this situation is to take out the carrier frequency, much like what we saw with the rectification, where it cuts the signal in half. In this situation, what the diode is going to do is it's going to remove the carrier frequency, or cut the carrier frequency in half, and then leave only the audio frequency left. And then we're going to have a capacitor here, a low pass filter, that's going to take out whatever's left of that carrier frequency and give us only the audio frequency that's left from the carrier signal. And then we just listen to the headset, and then there you have it. You have audio that you can listen to. The next thing that diodes can be used for is frequency multiplication. I'm not going to go over that because it's not really pertinent to anything I don't think we would do, but if you're interested in that, you're more than welcome to. Signal mixing, again, I don't think we're going to leave that. Switching, I want to cover because that's a major topic with diodes. So switching, you hear more often switching correlated to like switching transistors, like IGBT transistors have been, the most modern renditions of our most powerful switching transistors. But of course, transistors are based on diodes, so they go hand in hand here. So the ability of diodes to conduct in forward bias and to insulate with reverse bias makes them useful for switching in some electronic applications. Diodes can perform switching operations much faster than mechanical switches. And that's one of the biggest kind of advancements that we've had with electronics, though it might not be known. That's what's kind of funny about this whole thing, is that, again, we can kind of look at some of electronics, a lot of electronics we can look at in a mechanical sense. It's just that it's doing what mechanical operations would do with respect to electrons, and oftentimes it's doing it faster. And part of the reason why I can do it faster is because we can get electronics to operate at certain frequencies, and we can boost up frequencies, and the faster you have the frequency, the faster the components react. Therefore, you can have things, happening at gigahertz, right? You can have things happening at millions of times a second, right? Or hundreds of millions, it's just going up and up and up. So that's our switching. Again, I think switching will be more apparent when we talk more about transistors, but I just wanted to mention that. Then we have the voltage regulation, which we talked about earlier, but we can talk a little bit about this here as well. Most diodes have an avalanche breakdown voltage that is much higher than the reverse voltage ever gets. The value of the avalanche voltage depends on the diode, how the diode is manufactured. Zener diodes are specifically made So they exhibit well-defined, consistent avalanche voltages. Again, so the purpose of the Zener diode is to have that breakdown. And this is a depiction of the Zener diode. I was going to draw it earlier, but I knew there was going to be a picture of it here. So here it is. That's how we know the Zener diode is a Zener diode, because of that curve, which the reason why it's there is it's replicating the avalanche curve, if we see that. So that curve, you see the curve there, it's just like the avalanche curve. Okay, so that is the symbol for a Zener diode, and it kind of looks like a Z. So this is how a Zener diode is going to be used for regulation. So suppose a certain Zener diode has an avalanche voltage, also called the Zener voltage, of 50 volts. So we have a Zener diode that has an avalanche voltage of 50 volts. If the reverse bias is applied to the PN junction, the diode acts as an open circuit as long as the bias is less than 50 volts. Okay, so open circuit basically means it's not conducting. Okay, as long as the voltage is less than 50, it's not conducting. But if the reverse bias reaches 50 volts, even for a brief instant of time, the diode conducts. So once it hits that 50 volts, then the diode conducts. This effectively prevents the reverse bias voltage from exceeding 50 volts. Okay, so that is how a regulator operates. Basically, the diode won't pass anything other than that specific voltage that it was manufactured for. Okay. Anything less than that, it won't conduct. Anything more than that, it won't conduct. The current through a Zener diode as a function of voltage shown in figure 20-6, the Zener voltage is indicated by the abrupt rise in the reverse current as the reverse bias voltage increases. A simple Zener diode voltage limiting circuit is shown in figure 20-7. Note the polarity of the diode. The cathode is connected to the positive pole and the anode is connected to the negative pole. Okay, so basically this is just, it's basically in parallel with our circuit, and that's what's going to cause it to either act as a short circuit or an open circuit. Now let me just say this, that oftentimes people refer to this as when it hits the avalanche voltage or the breakdown voltage or its Zener voltage, that that it's acting like a short circuit. But that's not that don't mean that literally, because it's not a complete short circuit, because there's still resistance there. Okay, all they're saying, it's more precisely that's the point at which the diode will conduct. Okay. Now, at any other point, it's acting like an open circuit, which means it's not conducting. The next thing that diodes are used for quite commonly is amplitude limiting. And I'll just talk about this briefly. It's something called clipping, or having a clipped signal. So what you see here is two diodes that are opposing each other. So they're put in parallel with a signal, and they're put in parallel with a signal in opposition to each other. And the reason for this is, what we're going to get out of this, so here's the opposing signal. What we're going to get out of this is the peaks of our signal will be chopped off, essentially. Now, if you're looking at this, you can probably see what might happen and why we might want to use something like this. If we had, in the dashed line, what we see is a sine wave, but as it's clipped, that's how we get our something like a square wave, right? If we do a little bit more, you can do some filtering. You could change the timing of the circuit. You would get a little bit more of a square shape. So this is a way that we could even, have like a square waveform if we wanted to using a clipped a signal. A little fun fact: clipping diodes are often used in like guitar distortion pedals. That's what's happening. So if you haven't thought about this before, but in electronic sense, again, I always relate things back to audio a lot of times because that was my thing. So in an audio setting, let's say like a guitar distortion pedal, the idea is really just to build like a really bad amplifier, and part of that is to take a clean sine wave and then turn it into a square wave, because that's going to be harsh, right? The sine wave is smooth peaks and valleys, but then you give it these corners and you make it more harsh. Okay. Frequency control, I'm not going to go into that. Then he goes into some other things: oscillator, amplifiers, gun diodes, tunnel diodes. You can definitely review those if you're interested. I'm just going to go over the main ones here. LEDs, I think we're all familiar with that today. Light emitting diodes, okay. So those are the ones that have the gallium in them. Digital display diodes, the LCD. Photosensitive diodes, I think these are pretty interesting for those that maybe if you're not familiar with them, but if you have like any outdoor devices, things that turn on when the sun comes up and stuff like that, they're using these photodiodes, okay? So photodiodes are basically diodes that respond to, photons, so they respond to light, okay? Then we have the opto-isolator, which is similar to the photodiode. It's basically a way, it's kind of interesting, it's a way to basically isolate two stages of a circuit through putting an input through this device, and then the next stage will receive that signal, not through the electrical connection, but basically through the light, okay? And we'll get more into that later, why something like that might be favorable. It has to do with something called coupling in circuits. Sometimes we want to decouple our devices from each other, or certain stages of our device from each other. You're kind of seeing this, and he talks about this in some of this. You might start to see this, that sometimes people might think, well, of course we call it electrical engineering or electronics engineering, or electronic circuit design, and they say, well, it might not seem so much like engineering to you, because it seems like I don't know, there's a bunch of components that were specifically made to achieve a certain task, but there tends to always be a downfall to an imperfection within a device that we use in electronics, just like anything else. Okay, and he talked about this earlier. I didn't review this section, but he talked about how diodes tend to be nonlinear. What that means when they say nonlinear, it means that what you put in at point A, you don't get the exact thing at point B. Okay, and then so our job as electrical engineers is going to be to keep that integrity of that signal or of that power source the same. Sometimes we want to change it, but most of the time we might want to keep it the same. We want to keep that integrity the same, and that's no fault to the devices. It's because of things more having to do with the more minute physics, like parasitic capacitance, parasitic resistance, parasitic inductance, that will change parts of that signal or waveform as it passes through a certain device, and then we basically will work to reconstruct that signal to get it in its purest form. Okay, and decoupling. The reason why I mention that is because decoupling has a lot to do with that, because it has to do with encountering certain areas in a circuit where you might have a mismatch of impedance, and it might be difficult to match those impedances any other way. So you might use something like this opto isolator, to where you can separate those impedances, but you can still preserve that signal that was there. Okay, because not all devices want to talk to each other, and we'll break that down more and more. But you'll start to see, when we start to break down different circuit diagrams, you'll start to see, you know, how a complex circuit might seem like a lot, but then when you break it down into stages, you'll see, okay, why these components are there. Oftentimes they're because, you know, we had to put this stage in. Stage one had to be there to do this, but then as a derivative of using stage one, it ended up having a high impedance. So then we had to take it down and use stage two to bring it back down to a low impedance. And then, you know, we had to change another parameter. And if we change that parameter, then this parameter went up. So we have to bring that parameter back down. And that's how electronics kind of flows. Okay. So it's getting an effect, a cause and effect chain, right? You cause one thing to happen, but then there's an effect that's not favorable. Then you correct that, and then there might be another effect that's not favorable until you get to the end of your circuit. The end of the circuit is typically when all that stuff has been ironed out, and everything is basically linear, is what we would say, right? So it starts out non-linear, and then we basically try to linearize the whole operation there. Then he goes into photovoltaic, which is basically our solar panels. So not too much there to talk about. I think everyone's pretty familiar with solar panels. Again, if there's anything here you want me to talk about in more detail, I will. I think the next thing we're going to do is to go through some of these quiz questions in the next video. And then we'll see what we have for the next chapter. It's very plausible that we might go on to transistors. We talked about power supplies already. I want to go through some of these quizzes with you guys, walk through some of these questions with you, and then I'll keep going on the power supply. I have already started, coming up with the schematics, what I'm doing right now is I'm actually pulling components, trying to figure out what components I want to use, and then we'll walk through the schematics. We'll do a couple simulations of the schematics, and then I'll build it, I'll test it, and then, like I said, we might even eventually get some PCBs thrown out there and all that kind of thing. So I appreciate you guys for watching, and I'll see you soon.